Today we're going to talk about simplifying radicals, squares, and cube roots. These are your notes for simplifying radicals, square, and cube roots. First thing we need to do is we need to go ahead and talk about what all of this is here at the top of the page. So we have different definitions for the different parts of this. The first things first, the symbol, we call that a radical sign. Go ahead and label this just the way I am. And underneath or within the radical sign, we call that the radicand. And finally, we're going to be dealing with what we call indexes. And that's what we call that N there. That's the index. When we're simplifying radicals, squares, and cube roots, there's three conditions that we have to meet when we simplify them. The first condition is no radicands have perfect square factors other than 1. Please write this down. Factors other than 1, because 1 is a perfect square factor. The second one is no radicands contain fractions. Fractions. And this will all be explained as we go through the notes. But I'm just kind of letting you know up front what we need to do in order to simplify radicals. And finally, no radicals appear in the denominator of a fraction. And I hope you are writing all this down. If you need to, pause it. That's the nice thing about YouTube. So those are our three conditions that we're going to have to meet. So here we have, this is straight from your textbook, which you will be receiving, product property of square roots, where it says if we have the square root of A over B, it's the same thing as saying, the square root of AB, it's the same thing as saying the square root of A times the square root of B. For example, the square root of 4 times 9 is the same as saying the square root of 4 times the square root of 9. Okay, so let's go ahead and let's work on condition number 1. That's the first thing that we want to do. Let's work on condition number 1, square roots. Here we have the square root of 48. And when I'm thinking about the square root of 48, initially this is where my thought process goes. I think of the square root of 4 times 12. Okay, that works, but I also know that the numbers I can multiply together to make 12 are 3 and 4. So I'm going to go ahead and break that down a little bit more and say that's the square root of 4 times 4 times 3. And if you multiply 4 times 4 times 3, you'll end up with 48. Now what I can say is the square root of 4 times the square root of 4 times the square root of 3. The square root of 4 is 2. The square root of the other 4 is 2. And the square root of 3, that can't be changed into anything other than, sorry about that, that can't be changed into anything other than the square root of 3 or an irrational number. So we're going to leave that in that form. So we'll have 2 times 2, which is 4, times the square root of 3. And that's it. That's your answer. 3 times the square root of 20. We have it for example number 2. 3 times the square root of 20. I'll leave that 3. And I'll say the square root of 20 is going to be 4 times 5. Since 5 is a primary number, I can't go any further, and I know 4 is a perfect square number. So I'm going to say 3, this equals 3 times the square root of 4 times the square root of 5. Square root of 4 is 2. So I have 3 times 2 times the square root of 5, because if 5 can't go any further, it would turn into an irrational number. 3 times 2 is 6, so I end up with 6 times the square root of 5. Next, I have negative square root of 108. Now the negative sign is on the outside of the square root symbols, so we're not dealing with imaginary numbers. So when I talk about the square root of 108, I actually had to, do a little bit of math and figure out that the numbers that go into that, we're on problem number 3, the numbers that go into that are the square root of 4 times 27. And so 4 is a perfect square, but I think I can break down 27 even a little bit more. So I have the negative square root of 4 times 9 times 3. Now I can say square root of negative square root of 4 times the square root of 9 times the square root of 3, which that's 2. That's 3. That's an irrational number, so we'll leave it as is. So our answer is going to be negative 6 times the square root of 3. That negative sign just comes along for the ride. If it's a negative square root at the beginning, it's going to be negative at the end. Finally, we have this weird thing here, 49 to the 1/2. Okay, this is a way of representing roots as well. You will probably see this more in higher math, but we want to go ahead and expose it to you now. You never know if you could see it. And there's a rule that you need to know. If I have my index of n, my radical symbol, and my radicand of x, that is the exact same way of saying x to the 1 over n. So my n went from out here. Now, it's not shown here with our square roots, but our index for square roots is actually a 2. It's just understood to be a 2 initially. We use our indices basically when we go into cube roots and further like that. But the index is understood to be a 2 when we're dealing with square roots. So 49 to the 1/2 is actually the same as saying the square root of 49. It's the exact same thing. So all we need to do for that is just plain and simply say 7. If you would, please go ahead and take a little bit of time and write down any reflections or anything that you see from this that you feel like you need to remember. Go ahead and pause now. The next thing we want to go ahead and talk about is we want to go ahead and talk about condition 2 and condition 3. No radicand contain fractions. No radicals appear in the denominator of a fraction. So the first thing we need to talk about is the fraction part. And you can see where it says if it has the square root of a over b, that's saying the square root of a over the square root of b. And that's how we would go ahead and represent that. That square root symbol can be broken up into the numerator and the denominator. We also have an example over here of simplifying where it says 2 over the square root of 3. And we're going to practice on this. Now, the thing that we see is condition number 3 says no radical symbol can be in the denominator of a fraction. And we have a radical symbol in the denominator of the fraction. Now we want to use our rules for fractions that remember whatever we multiply to the top, we multiply to the bottom. So we can go ahead and the fraction will remain the same. So the value of the fraction will remain the same, I should say. So we can go ahead and multiply both the numerator and the denominator by the square root of 3. And we end up with 2 times the square root of 3 all over 3. And we'll talk about that a little bit more when we get to problem number 10. So let's go ahead and start here with number 5. Number 5 shows the square root of 7 7/16. Again, we can't have a radicand cannot contain a fraction. So we're going to go ahead and simplify 5 as the square root of 7 over the square root of 16. Now that's pretty simple to go from there. Since if we took the square root of 7, that would just end up being an irrational number. We're not going to do anything to that square root of 7. But the square root of 16 can simply be reduced to 4. And that's our answer. For number 6. I'm looking at it upside down, I guess. For number 6, we have the square root of 18 over 3. So we're just kicking it up a little notch here, and we can look at this and say, okay, let's break that 18, just like in the problems that we did on our first page. Let's go ahead and break that up, and I'm going to say the square root of 9 times 2 all over 3. The square root of 9 we know is 3, so I have 3 times the square root of 2. And if it's okay with you, I went ahead and I skipped that step of saying the square root of 9 times the square root of 2. And I just went ahead and I simplified that 9 and went straight to 3. If you have an issue with that, please mark here on your paper and we'll talk about it in class. And I'm putting it all over 3. Now we're looking at this like it's a fraction. And as you can see, I have 3 in the numerator, 3 in the denominator. Those can go ahead and cancel each other out. So our answer is just the square root of 2. The square root of 80 over 45 over 45. So again, for number 7, I need to break this up. I have the square root of 80 over the square root of 45. And so now I'm going to go ahead and break this up. And I'm going to say, and I'm just really, to be honest with you, I'm just thinking about what are the multiples, what are the factors of 80, what are the factors of 45. And initially when I thought about it, I thought, okay, 4 times 20 makes 80. You may have come up with other numbers. Excuse me, that should be a 20. 4 times 20. Again, you may have come up with other numbers, and that's perfectly fine. And for 45, I know I have the square root of 9 times 5. That 20 can be broken up a little bit more. So I'm going to go ahead and say the square root of 4 times 4 times 5 all over the square root of 9. times 5. Now I know the square root of 4 is 2. The square root of 4 is 2. So I'm going to go ahead and say 2 times 2 times the square root of 5 all over 3 times the square root of 5. And I know that 2 times 2, because of space restrictions, I'm going to go ahead and change that into a 4. Now, all of a sudden, I'm thinking, okay, now I have to deal with the radical symbol and the denominator. But again, we have a fraction. Let's go ahead and reduce before we get ahead of ourselves. So this 5 cancels, the square root of 5 cancels, this square root of the 5 cancels. And all we're left with is 4 thirds. Again, anything that you're seeing in the notes that you're having a hard time understanding, please put a mark beside it so we can go over it in class. For number 8, I have the square root of 20 over 4. Again, it's not that bad. Let's see. Square root of 20 is the square root of 5 times 4, or 4 times 5. Remember, commutative property says I can put it in any order. All over 4. So I end up with, let's see, 2 times the square root of 5 all over 4. I went ahead and took the square root of 4 and said that was 2. That's how I have 2 times the square root of 5. 5 can't be changed into, there are no perfect squares in 5. All over 4, I can reduce it now. 2 goes into 2 one time, 2 goes into 4 2 times. So I end up with the square root of 5 all over 2. For number 9, it looks a little tricky, but I swear it's not. It's pretty much what we've been doing. I have 8 times the square root of 3/4. So remember, is this 8? Remember, when we're multiplying fractions, we can represent 8 as 8 over 1, correct? And then we can go ahead and multiply. So I'm going to rewrite this as 8 times the square root of 3 all over the square root of 4. So now I have the square root of 4 is 2, so I have 8 times the square root of 3 all over 2. 2 goes into 2 once. 2 goes into 8 4 times. And I end up with 4 times the square root of 3. Okay, for question number 10, for example number 10, this is where we're going to start dealing with our third condition. No radicals can appear in the denominator of the fraction. So when I'm looking at 10 here, I have the square root of 35 over the square root of 15. And before I do anything, I want to go ahead and reduce this fraction, because 5 goes into 35, 5 goes into 15. So this actually is the same as saying 7 over 3. That makes it, remember, there's all these rules that we need to consider before we go any further. So let's go ahead and do this one. So we have the square root of 7 over the square root of 3. Okay, now remember when we were adding fractions. When you add fractions and they have uncommon denominators, we need to go ahead and we need to multiply the numerator and the denominator by the exact same number. That way we can go ahead and add them. Well, that rule actually applies to this as well. It doesn't change the value of the fraction, it just changes how it's being represented. So what I can do is I'm going to multiply this entire fraction by the square root of 3 over the square root of 3. So I'm multiplying the numerator and the denominator by what's represented in my denominator. And the reason why I'm doing this is I'm going to work this a little bit backwards so we can see. I end up with the square root of 7 times 3 all over the square root of 3 times 3. So now take it the next step. I end up with the square root of 21 all over the square root of 9. That gives me the square root of 21 all over 3. And that's it. You might look at that 21 and that 3 and say, okay, I need to go ahead and reduce that because 3 goes into 21 7 times. No, you can't. That's the square root of 21. So you can't reduce it from there. If you would, please go ahead and pause the video and write down any questions or any things that you feel like you need to remember at this time. Finally, we have cube roots. For cube roots, it's saying what number can multiply by itself 3 times in order to make that number. So if I have the cube root of 64, if I'm not mistaken, on question number 11, I say 4 times 4 times 4 makes 64, so the answer is just plain and simply 4. When I get to the cube root of 16, I'm going to go ahead and I'm going to rewrite that as cube, don't forget your index of 3, the cube root of 8 times 2. And we talked about this a little bit in the last class where we said the cube root of, we named some perfect cubes. And so we know that 8 is a perfect cube, so I'm going to end up with 2 times the cube root of 2. For number 13, again, we're just doing pretty much the same thing we did on our first page of notes, except we're considering it in cube form instead. The cube root of 24, again, the cube root of 8 times 3. So I end up with 2 times the cube root of 3. Now, here's the thing with cube roots. We were talking about negative square roots when you had the negative sign in the radicand, with the radicand, and we said that that would be imaginary. But when you're multiplying the same number by itself, it can be a negative number. For instance, if I had the cube root of negative 64, the answer would just be negative 4, because negative 4 times negative 4 is positive 16, but positive 16 times negative 4 would be negative 64. So here, this can work. So let's go ahead and look at this problem. When I did the cube root of negative 162, I thought about, I was just, doing some math in my brain, and I knew 162 because that's not a number that easily came to me, I'll be quite honest with you. Initially, I thought about, okay, the cube root of 2 times 81. I just divided the number by 2. But I thought, okay, that's not going to necessarily work for me, so I'm going to say the cube root of 2 times, and I know 9 times 9 is 81, so I said 3 times 3, there's one of my 9's, and 3 times 3, there's my other 9. So there's my 9 times 9. There's my 9 times my 9. Now I'm going to go ahead and pull out 3 of those 3's. So what I end up with as my answer is going to be negative 3 times the cube root of 6. Don't forget, ooh, I forgot that on the previous problem. Well, we want to make sure that we include the cube root of 6. Now, again, we said that the index is the same as putting it in. Remember, we talked about the way to represent it. We could represent it as a fraction, as an exponent, or as the cube, as the index. So for number 15, I went ahead and I thought about some numbers. Again, what makes 750, and a number that came to my mind. You might think about different numbers, and that's perfectly acceptable. I thought about, okay, 25 times 30. So the cube root of 25 times 30. Well, I can break that down, and I can say the cube root of 5 times 5, there's my 25, times 5 times 6, there's my 30. And now I have those 5's right there. Don't forget my index of 3. So there's my 5's. So my answer is going to be 5 times the cube root of 6. Now, the final page of your notes gets into those imaginary numbers. If you would, please, what I'd like you to do is to take a look at this, explore it on your own, and see if you can come up with anything on your own. We'll talk about this in class. Thank you.